Alrighty, hello, and excuse me, welcome to office hours this evening. Before I open things up to questions, I got a request by email, kind of expressing a little bit of uncertainty on how to approach eLab 5. Sorry, I'm just pulling up the yeah. So anyways, I'm going to start off. Totally will be taking live questions for almost the whole thing, but I'm going to start by doing a mini kind of lab lecture on experiment 5, just to kind of present a little bit of background and kind of give everybody what's the word I'm looking for, a starting place more or less on how to approach these calculations and all that good stuff. So the objective for, oh wait, hang on. I need to open a new layer. There we go. Okay, so the objective for this experiment is we are going to use the ideal gas law to determine the molecular weight of a volatile liquid. Hang on. Volatile. Amanda, the grade for the grade that is currently displayed is not. I need to go and grade all the free response questions by hand, which I know I'm definitely behind. I actually just started working on grading the free response questions for lab quiz 1. So I'm behind, and I know I'm behind, but I'm starting to climb out of that grading black hole. So and I will, by the way, I will post as I finish each quiz. I'll post an announcement on Canvas, so you guys aren't left in the lurch wondering, like, has this been graded? Is this my final grade on this, or is it not? I'll post on Canvas so you will know when those have been updated. Yeah, totally. You are so welcome. Alrighty. So let's. Okay. Yeah. Sorry. Can I say so more than I already have? I don't think it's possible. All right. So the objective for Lab 5 is we're going to use the ideal gas law to determine the molecular weight of a volatile liquid, and so for starters, let's talk about what this means. What is a volatile liquid? And a volatile liquid. Sometimes you hear the word, you think it might be explosive. You're like, oh, that person's volatile. In the context of chemistry, volatile means a volatile liquid has a low boiling point. So water is not a volatile liquid. It boils at 100 degrees Celsius, right? That's 212 degrees Fahrenheit. It takes a lot of energy to get water into the gas phase. A volatile liquid, it does not take a lot of energy. An example of a volatile liquid is nail polish remover, right? Acetone. If you have any experience with it at all, you know that it evaporates just at room temperature. You like squirt it, or if you spill some, it's dry, a few moments later. And so the kind of experimental design is for this experiment. We'll get to the design, but I just wanted to address what a volatile liquid was. And it's a liquid, so it's easy to handle, right? Gases are hard to handle. But because it's low boiling, we can have it enter the gas phase without putting forth a ton of effort. Now, I'll talk about kind of the background and what is done in this experiment. But first, I want to explore how we're going to use the ideal gas law to determine the molecular weight. So the ideal gas law is PV equals nRT, right? And molecular weight also has an equation. Molecular weight is equal to the grams divided by the moles, right? It's grams per mole. Now, the one variable that these two equations have in common are moles, all right? So if we isolate moles in one, we can substitute into the other, which is exactly what I'm going to do right now. I'm going to multiply both sides of the equation for molecular weight by moles over molecular weight, and you'll see why in just a moment. You'll notice that molecular weight cancels on the left side of this expression, and moles cancel on the right side of the expression. So we get a new or rearranged expression. The moles of a substance equals the mass divided by its molecular weight. And now we can substitute this into the ideal gas law. You'll notice that when we do, we get the expression PV equals our value for N. Moles from the equation for molecular weight is equal to grams of that substance divided by the molecular weight times RT. Now, if we take this expression and we solve for molecular weight, first multiplying both sides of this equation by molecular weight, molecular weight cancels on the right side of the equation. We get molecular weight of a gas times pressure times volume is equal to the grams of that gas times R times T. And now we can divide both sides of this equation by PV. Pressure and volume cancel out of the left side of this equation. And now we get a new algebraic expression. The molecular weight of a gas is equal to the mass of that gas times the ideal gas constant times temperature divided by the pressure and volume of that gas. All right? So, if you know the mass of that gas, of a gas, the temperature of the gas, the pressure of that gas, and the volume, if you know these four quantities, you can calculate the gas's molecular weight. All right? So that is the kind of theoretical background, we have 4 quantities to collect: grams, temperature, pressure, and volume. Now, temperature you measure with a thermometer. That is not difficult to measure. All right. Pressure is measured in a lab context with a barometer. So again, that's just looking at a dial, reading off the pressure. There you have it. What's a little trickier is measuring the mass and the volume. All right. The method that we're going to use, or that this experiment employs, is you have a little bit of your gas, or sorry, not your gas, your liquid, right? This is a volatile liquid, and it's covered with aluminum foil with a small little hole. So some gas can escape. And what you do in this experiment is you heat it. You heat it so that the liquid inside your container goes from the liquid phase to the gas phase. So you heat this until you don't see any more liquid at the bottom, and any excess gas escapes, which is good. That's why that hole is there, because we want to know how much gas is we want to know how much gas it takes to fill this volume. Then what you do, once it's all evaporated, is you stop heating and you actually cool. You cool it back down, and you condense it from the gas phase back down to the liquid phase. Right, so you start as a liquid, you vaporize it, but then you go back to the liquid phase. And the reason is this: you measure the mass of this liquid, because all of that liquid used to be the gas filling the container. So this mass is equal to the mass of the gas. All right? So that's why the experiment talks about heating your volatile liquid. Then once it's all evaporated, you cool it back down, because you want to get the mass of all those particles that used to be in the gas phase. It's easier to measure when it's in the liquid phase. So here, you measure that mass with a scale. All right? So that's how you get the mass. Now the question is, how do you measure the volume? Right? How do you measure that volume? And the way you do is you take the container that you had when it's empty, and you fill it with water. Which I'm going to use this orangey color. I should have saved it blue, right? But what can you do? You fill your container with water. Oops. And then you fill up the volume of your container with water. And then what you do is you measure you record the grams of water and you look up the density of water. And with these two things, you can find the volume of water. And here's the beauty is water is occupying the same volume that your gas occupied when you vaporized your volatile liquid. So the way you get your volume, because again, remember density is grams over volume. So volume is equal to grams over density. All right, the way you get your the volume is you get your volume of gas because it's equal to the volume of water. You filled it with water and you measured the mass of water and divided that by the density of water. So you measured this, you looked up density, and that's how you get your volume. And then you can take these four quantities and calculate your molecular weight. So that's an introduction and kind of how you're going to approach working Lab 5. If you have more questions about it or specific steps or whatever, totally hit me up. I'm totally happy to answer. But I just got an email request for requesting further explanation on how to approach the calculations for Lab 5, and this is the step-by-step breakdown. All right, and with that being said, now that we've gone over eLab 5, I'm ready to take any questions that you may have. All right, Kate, let's see. So we're using the mass of the empty. Yes. That is correct. The way you measure a mass in a lab context is almost always you take the mass of an empty container and then the mass of that container with the substance inside of it, and then you take the difference between the empty and the full containers. That is 100% correct. Anytime. Ludwig, let's see. Are we subtracting? You know, let me, Ludwig, let me check to see, let me check to see what is in the, what data, what data you're given. Because I don't remember off the top of my head. So let me check this out. Let's see, so you're given the mask of the empty. Oh wow, these are long. Okay. Here, hang on. So I'm seeing what's written in the spreadsheets. Some of these names are quite long. Okay, let's see. Oh, you know what? Okay. Yes. Ludwig and Kate. So I'm looking at the I'm actually looking at the data spreadsheet right now, and I didn't put this 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 particular lab set together. So actually, so what? Sorry, when I was lecturing and telling you like, oh, this is how you find the volume. That's how you would have done it in lab. But turns out that in the data spreadsheet, turns out your volume is just given. So so you don't actually have to do any of those fancy calculation stuff, because it just tells you the volume of the flask in milliliters, which is awesome. And so to find. Yes, Jason, that is correct. The volume of the flask that's given is equal to the volume of the gas, and they just give that to you. You don't have to do any of those calculations that I just said you did. And then Kate, what you said, the mass of the sample plus the aluminum foil plus the band minus the mass of the aluminum foil. So I think there's actually a couple. So the way you get the The way you get this guy the way you get your grams is you are given the mass of the aluminum foil plus flask plus rubber band plus sample after cooling minus the mass of the aluminum foil plus the flask plus the rubber band. And that difference there is the mass of the sample. In other words, the gas. So yeah, so just taking the difference between those two will give you the mass of your sample of gas. Okay, let's see. Okay, for the purpose of this lab, would you like us to input our data analysis values? Oh, yeah. Ah, Ludwig, great question. Dude, anytime. All right, Kate, let's see. Would you mind giving a review? Oh, yeah, not at all. Not at all. So percent error is it's one of those things that just keeps keeps coming back. So you can calculate a percent error for any quantity, and it's equal to the absolute value of the correct value minus the experimental value divided by the correct value times 100. So, for example, let's say that that you're doing a lab, and the let's say the molecular weight of your volatile liquid is 56.37 grams per mole. But let's say you calculate that the molecular weight is 49.88. All right, the percent error here for your calculation would be the correct value, which is 56.37 AMU, absolute value of that, minus your experimental value, right, what you got from your data, divided by the correct value, times 100. All right, so we've got 56.37 minus 49.88 gives us, my calculator says it's 6.49 AMU over 56.37 AMU times 100. Now you'll notice, if you're keeping track of sig figs, both of these numbers have their last significant digit in the second decimal place, as does our numerator, so we don't need to round. It has the proper number of sig figs. We go 6.49 divided by 56.37 times 100. So this would give us a percent error of 11.5%. Yes, that is correct. Yep, gotta keep track of the little details. Ludwig, I so totally can. Give me a second to pull it up and we will dive right in. Let's see. Chapter 6, number 53. All right, almost there. It's just logging me in and loading the page. All right, let's see, number 53. Oh, wait, let me just make sure I'm in, chapter 6. Because I don't want to work number 53 from another chapter. Okay. So, the air within a piston equipped with a cylinder absorbs 565 joules of heat and expands from an initial volume of 0.10 liters to a final volume of 0.85 liters against an external pressure of 1 atmosphere. What is the change of internal energy for the air within the piston? Okay. So, give me one second. I'm just going to recreate the problem here. So we're told that we're in a piston. The air absorbs 565 joules of heat. And expands from 0.10 liters to 0.85 liters against 1.0 atmospheres of pressure. And then we're asked, what is the change in internal energy for the air? Or I should say, the air in the piston. Question mark. Okay, so first thing we got to identify is what we're after, right? What we're trying to find. And it says it right here. What is the change in internal energy? They want to know what delta E is. All right, now delta E, we know, has an equation. The change in energy is equal to the energy transferred through heat plus the energy transferred through work. Now we know that both Q and W, thermal energy and work, have their own equations, right? So these may come into play, they may not, but I like to write them out because often it's useful. Now let's look at what we're given in this problem. First, we're actually told that the piston absorbs 565 joules of heat. That heat means that they're giving us a value for Q. So the first thing they give us is actually straight up Q is equal to 565 joules. So we've got Q, which means we don't even have to worry about this equation. Now we just got to find how much energy is transferred through work. Let's look at what else they give us. They give us an initial volume. They give us a final volume. Together, we can use these two quantities to find our change in volume, right? That's this quantity. And they give us the external pressure against which this gas is expanding, which is 1 atmosphere. So we know this as well. So we can calculate work. Then we can calculate our change in energy. Work is equal to -1 times our atmospheres times our change in volume, which is final 0.85 liters minus initial 0.10 liters. So work is equal to 1.0 atmospheres times, if you punch this into your calculator, the difference is 0.75 liters, and you'll notice that the last sig fig in each of these numbers is in the second decimal place. The last sig fig in 0.75 is in the second decimal place, so we do not need to round. We do not need to add a 0. You multiply this by 1, and you get work is equal to 1.0 times 0.75 is 0.75 liter atmospheres. So now we have work. We just got to add it to Q, but there is a problem. Q was given to us in joules. Our energy transferred through work right now is in liter atmospheres, so we need to do a unit conversion to convert between liter atmospheres and joules. And I believe, let me just double check. Whenever you're not exactly sure of a unit conversion, just Google it. Liter atmospheres to joules. I think it's 1 liter atmosphere is 101.3. Yeah. 1 liter atmosphere is 1.3 joules. Liter atmospheres cancel. And so we get 0.75 times 101.3 comes out to be 987.675 joules. We can only keep 2 of these sig figs, but I'm going to wait to round till the very end after we calculate our change in energy. So we have 565 joules plus 987.675 joules. You add these together and you get 1,552.675 joules. Sig figs, we've got a round to the tens place, and 2 is going to round down. So the change in internal energy for the air in this piston is 1,550 joules of energy. Oh, hang on. I forgot. Nope. Okay, I made a major mistake. I made a major mistake right here. Let me just double check the problem. Make sure that that's the only mistake I made. Initial volume of 0.1, final volume of 0.85. Yep. So this should be a negative. This should be a negative. This should be a negative. So this is not a plus sign. This is a minus sign. So let's try this again. We've got 565 minus 987.675. That is a negative 422.675 joules. And we can only have 2 sig figs. This 2 will round down, so our change in internal energy is a negative 420 joules. How about that as a correct answer? All right, that is the correct answer. So that is how you tackle Chapter 6, number 53. Dude, anytime. Thanks for making office hours a more lively place. Ludwig, I am so glad. I honestly feel like it's underutilized by students, and I I think that there's a lot to be gained from the interaction, from trying problems on your own, then bringing them, seeing them worked out, and I really do wish that that more students would take advantage of it. But I'm so thankful for those of you that do, because I want to be here. I want to be available. I want to help you guys through. And so I think this is the closest we get to that in-person interaction that we had in the before four times, right? When we could all be in a room together talking about chemistry, solving problems. I think office hours is the closest we get to that place. And I really enjoy it, but only because you guys show up and make it so awesome. Let me see. Did I totally mess up my calculation? Jason, let me double check. Holy moly, I could have just totally botched this thing. Let's see. 101.3 times 0.75. Yeah. I don't know what went wrong. I don't know what went wrong. Maybe it was one of those things where my calculator, I forgot to clear my calculator, because yeah, you are absolutely right. Okay, so second amendment to this problem. Holy moly. Third time's a charm, right? Okay. So this is negative 75.975 joules. Sig figs wise, we can only keep 2. All right, then adding 565 gives us 489.025 joules. Only keeping 2 sig figs. Oh, no, not 2 sig figs. So we got to look at the last significant digit, which is in the ones place, 2 rounds down. So our answer, which is not negative, is 489 joules. Jason, thank you. You are totally right. Oh, let's see. If black is the absence of color, how does that relate to our lecture today regarding light? Ah, okay. Ludwig, great question. So, wherever you see black, or where I see black, that black, you're totally right, is the absence of color. And so when we see something as black, that's our mind filling something in where we're getting no light input. So I'm looking at my phone right now, which is, I've got a black phone. And the reason why I'm seeing black is because literally the light that's coming out of the lamps right now hits my phone, and none of it is bouncing back into my eyes because that material absorbs all colors in the visual spectrum. All right, so all the light that's hitting it that my eyes can see visually, none of those colors are bouncing off and making it to my eyes. So your mind is filling in the color black when it receives no input, no light, when no light is hitting it from wherever that black object is. That doesn't mean that that black objects absorb or retain all the energy that hits them, but it does mean that they absorb and retain all the visual light. So it could be emitting or releasing light of wavelengths that we can't see with our eyes, but no light within the visible spectrum, i.e. light that our eyes can detect, is bouncing off an object that is black in color. And that's how it relates to what we were talking about in lecture today. Oh, Ludwig, great question. The answer is Ludwig, it totally can, and it actually does. So, like with hydrogen releasing light, specific wavelengths of light that we could observe, those are not the only wavelengths of light that hydrogen emits. There are tons more that are outside the visible range, and that's true for every atom. Turns out, though, there often are several wavelengths within the visible spectrum that we can see, and so that's because we could observe them. Those wavelengths helped us make the jump and pioneer the field of quantum chemistry, quantum mechanics. totally, Ludwig, I totally agree. I totally agree. It almost feels like ghost light or something, right? Because we can't see it because it's invisible. Um, I find it fascinating. Oh, let's see. Sorry, Ludwig, I'm just now seeing your question. Could you go over question 63 in the Chapter 6 homework? I absolutely can. All right, so let's take a look here. 63. The propane fuel used. Oh, hang on. Used in gas barbecues burns according to the following chemical equation. So let's see here. There we got propane, which is a gas, reacting with oxygen gas to produce carbon dioxide. That's 3 moles of carbon dioxide, 4 moles of water. Also in the gas phase, and they give us a delta H for this reaction is negative 2,217 kilojoules. This is kilojoules per mole. Sometimes the book will print delta H as being kilojoules, but it's always per mole. All right, now here we get into the meat of the problem. No pun intended. I just turned the page and they're asking about a pork roast. So if a pork roast must absorb one, oops, sorry, I want that to be in black, 1.6 times 10 to the third kilojoules of energy must be absorbed. Then they're asking what mass of carbon dioxide is emitted sorry, there's only one M there. While grilling. All right, and the linchpin to this problem is really understanding how delta H relates to this reaction. So because delta H is negative, that means this is an exothermic reaction. It is a reaction that releases energy. So we're going to write in energy as a product of this reaction. Because in addition to producing 3 moles of carbon dioxide and 4 moles of water, this reaction is also producing 2,217 kilojoules of energy in the form of heat. Now, we're told that it takes 1.6 times 10 to the third kilojoules to cook this pork. And we want to know, we're asking how many grams of carbon dioxide are emitted. So we need a unit conversion to convert from kilojoules of energy to moles of CO2. All right, once we have moles of CO2, we can convert to grams. Now, the ratio is for every 3 moles of carbon dioxide produced, 2,217 kilojoules of energy are also produced. So that is our energy to mole ratio. Kilojoules of energy cancel. We're left with moles of CO2. Next, we need to convert from moles of CO2 to grams. All right, and here we need a molecular weight. So we got to add up the mass of 1 carbon and 2 oxygens. It comes out to be 44.01 grams in 1 mole. Moles of CO2 cancel. And we are ready to crunch our numbers. So we got 1.6 times 10 to the third times 3 divided by 2217 times 44.01 grams. We can keep 2 sig figs. Well, here, let's write out our value. 95.285521. As I mentioned before, we can keep 2 sig figs. You can have your first 2. 2 is going to round down. So 95 grams of carbon dioxide are produced while this pork roast grills. So that is problem 63. What about the 10% part? Oh, let's see. Sorry about that. I totally missed it. So that's the amount. It takes that much energy to fully cook. And let's see. And okay, I'm so sorry, Ludwig. I totally missed this part. And if only 10% of the heat produced by the barbecue is actually absorbed by the roast. Okay, so here's the thing. Okay, so this is not our final answer, but it's a stepping stone to get there. So let's open a new slide. All right, so 95 grams of CO2 are emitted if the roast absorbs 100% of the heat. But the reality is it doesn't, all right? We were told in this problem, and I totally missed it at first, that the roast absorbs 10% of the heat. So if it's only absorbing 10%, that means that we need to take our 95 grams of CO2, and if we want to know how much is going to get emitted, if you have to heat it up only absorbing 10% of the heat, we've got to multiply this by 10. So 950 grams of CO2 are produced. And where this comes from it's just 100% divided by 10%. Right, so if it's only absorbing a fraction, then we need to use 10 times as much, or 10 times as much will be produced. Totally. Dude, and thanks for the catch. I totally spaced that that part of the problem. All right, Rin, sorry, I just saw your question. So, when determining the oxidizing and reducing states, is there ever an instance where they won't gain electrons? Okay. Okay, so here's the deal. Rin, this is true for every redox reaction. In every redox reaction, something gains electrons. And something loses electrons. All right, in every single redox reaction, this is the case. If electrons are not exchanged, it is not a redox reaction. All right, there are totally reactions where electrons are exchanged, but they're not redox reactions. So every time you're dealing with a redox reaction, something is going to gain electrons and something is going to lose electrons. So if you can't find something that's losing and something that's gaining, then you're not dealing with a redox reaction. And if you're not dealing with a redox reaction, there will not be an oxidizing and reducing agent. It's totally possible. And this is just food for thought. I didn't write any problems, and the exercise there are no problems where it says what's the oxidizing agent, what's the reducing agent, but it's not a redox reaction. It's a redox reaction every time we're asking you to identify. Every time we're asking you to identify an oxidizing agent and reducing agent. And I totally can. Let me pull up exercise. Excuse me. Sorry for the yawn. It is the mileage, not the company. All right, question. Okay. Okay, so okay, cool. I wasn't sure if it was like if there was one in particular that was okay, let's see. You said 25, 26. Okay. Here, I'm going to do so I'm going to do a problem similar to this, and I think that will give you the handholds you need to scale this wall. All right, let me find. I'm just gonna grab a new redox reaction. All right, so here's one that's actually kind of similar. So so this is not expired by, inspired by exercise 4. So here is the reaction. All right, and we are going to first assign all oxidation states to determine the substances that are oxidized and reduced, and then 3, we are going to determine the oxidizing and reducing agents. All right, so this is exactly what all of these problems are asking you to do. And we're gonna, lame. All right, hang on. I'll just rewrite the equation. Where was it? There it was. And this is solid zinc. This is aqueous. This is aqueous. And that is solid. Okay, so first off, we need to assign all of our oxidation states. And so looking at the first, solid zinc, it's going to have an oxidation state of 0 because it has a charge of 0. And we know that the sum of the oxidation states of every atom within a species adds to its charge. So charge is 0, zinc is the only atom, Zinc's oxidation state is 0. Next, let's move to silver, aqueous silver nitrate. Now, there's a trick for this, and it lies in remembering what it means to be an aqueous compound, an aqueous ionic compound. Specifically, an aqueous ionic compound means that you're dealing with a separated anion and cation. So silver is a cation with a charge of positive 1, which means silver in this compound has an oxidation state of positive 1. Oh man, I messed it up already. Hang on. Okay. That sorts that out. Zinc is 0. All right, so we have as I said before, silver cation and nitrate anion. Because silver in silver cation has an oxidation state of 1, silver and silver nitrate will also have an oxidation state of 1. Now looking at nitrate, between the two of them, oxygen is more electronegative, so it picks up a charge of -2. And now we can determine the charge of nitrogen because the oxidation state. Because the oxidation state of nitrogen plus the oxidation state of 3 oxygens will add to our total charge, which is -1. So nitrogen plus 3 times the oxidation state of oxygen is equal to -1. So we've got nitrogen minus 6 equals -1, which means nitrogen will have an oxidation state of +5. Oops. All right, now let's move to the product side. Again, we are dealing with an aqueous ionic compound, which means that our cation and anion are separated. Nitrate we've already looked at. Oxygen has a charge of oxidation state of -2. Nitrogen +5 in nitrate. Because we have 2 nitrates balancing with our zinc cation must have a charge of +2, which means its oxidation state will also be +2. All right, and then finally, silver on the product side will have an oxidation state of 0 because it has a charge of 0 and it's the only atom in the compound. So here are our oxidation states. To determine the substance that is oxidized and the substance that is reduced, we need to see which oxidation states are changing. And the two that jump out at me are zinc and silver. Let's start with zinc. Zinc goes from 0 to a +2, which means, so if you go from 0 to positive, you are losing electrons. Zinc loses electrons. And let's see, it's Leo says GR, lose electrons oxidation. That's Leo, gain electrons reduction. That's GR. So zinc, whoa, hang on. zinc is oxidized. Zinc is the substance that is oxidized. Now let's take a look at silver. Silver goes from +1 to 0. Which means if you go from a positive to 0, you have gained electrons. Which means that silver is the substance that is reduced. All right. So once you find that change in oxidation states, and there's going to be two of them, one thing will gain, one thing will lose. Once you've found the change, then you can identify the substance that is oxidized and the substance that is reduced. And in both cases, whenever you're going for the substance, right here, it's an atom. It's always going to be an individual atom. Whenever you are going after the agents, this will always be a species, a whole, whatever the reactant is. So it'll be whatever that reactant, it could be an atom, it could be an ion, it could be a molecule. Now let's return. So we've determined the substances that are oxidized and reduced. Let's focus in on zinc for a moment, and ask what reactant caused the oxidation? What reactant caused the oxidation? And the answer is the reactant that reacts with zinc to cause that oxidation is silver nitrate. So silver nitrate is the oxidizing agent. All right. Now, let's think about what gets reduced. Silver is reduced in this. You have to ask yourself, whoops, I don't want this to be yellow, I want it to be salmon. So silver is reduced. Ask yourself, what reactant causes the reduction? All right. And the reactant that causes the reduction is zinc. All right, which is just an atom. It's solid zinc metal. Because it is the reactant, we say that zinc is the reducing agent. All right, so that is an example of these kind of longer problems at the end of exercise 4. All right, you get the oxidizing agent. Well, first you assign the oxidation states, find the ones that change, That'll give you the substance. And whenever you're doing the substance that is reduced, it's just an individual atom. Whenever individual element is experiencing a change in oxidation state. And then once you've determined that, once you do that, then you can determine the agents, because you ask what reactant caused that to happen in the reaction. Okay, let's see. Oh, dude, you are so welcome. Okay, let's see. Just to clarify, if there's no charge listed on the metal. Yes. Oh, let's see another one. Ah. Okay, Rin, great question. So, Rin, here's the thing that you've got to remember. So if an element is by itself with no charge, so like in this chemical reaction, so you got to remember the 4 rules for determining oxidation states are like a flow chart. You first go to the first one, then bounce to the second, then the third, then the fourth. And rule number 1 says that the sum, so this is the first rule. The sum of all the oxidation states must equal the total charge. So if you look at the total charge on sodium when it's here by itself, it's 0. That means that sodium must have an oxidation state of 0. So before you jump to that rule 3 that talks about the main group metals, first you got to look at the first rule. If that can't help you, then you jump to rule number 2 about hydrogen, then rule number 3 about main group metals, finally the rule about electronegativity. So if an element with no charge listed next to it, like sodium, it would not be its ionic charge because the first rule says that all the oxidation states must equal our total charge, which in this case is 0. Where that rule number 3 helps, is assigning the oxidation states in sodium chloride, because sodium is our main group metal, so it will take an oxidation state of +1, and that allows us to find chlorine's oxidation state, which is -1. Totally. Totally. That is why I'm here. Oh, okay, let's see. Sorry, Ren, I just saw your question. An exercise 4 for 26. Okay, let me pull it up. Okay. Okay, for 26, would you use H2 in the product? Ah, okay. Okay, so yes, this is totally something that can happen. Okay, so here. So if you look at this reaction, and you look at hydrogen, hydrogen starts with a positive 1. And then on the product side, hydrogen and H2 has 0 and is positive 1 in sodium hydroxide. So this can be confusing. You can be sitting here looking at this going, is hydrogen reduced or does it stay the same? And the answer to your question is it doesn't matter if it stays the same. If there is at least one instance of the oxidation state changing, then you can say that reduction has happened to hydrogen. Not all of the hydrogens, but some of them. All right, so this would lead you to conclude that hydrogen is reduced in this reaction. It doesn't matter that some of them change the same. There are some hydrogen atoms that are reduced. Excellent question. You too, Rin. Thanks for dropping by. It would office hours would not feel complete without your customary 9 p.m. appearance. Alrighty, and that is going to do it for tonight. Thank you, everybody, for coming out, asking some great questions. Thank you, everybody who's watching after the fact. I hope you all have a great weekend, and I will catch you on Monday.